guys, all absorption spectrometers or spectrophotometers work basically the same way. There's quite a bit of variation, but the basics are this. You have to have a light source, because remember, you're shining light through your sample. Different light sources out there. You can have lasers that put out one wavelength, but most spectrophotometers will have a light bulb of some type that puts out multiple wavelengths. So you see our light bulb here putting out blue light with a short wavelength, red light with a longer wavelength, have green light in between. The light goes through something called a monochronometer. What's a monochronometer? It selects for a particular wavelength of light. In today's experiment, we're going to be working at about 400 nanometers. That's just on the edge of violet to ultraviolet light. So I'm showing it with blue. So the light goes through the monochronometer. You get all this blue light coming through. Let's say I have 3 photons of blue light coming through there. They hit my sample. Remember, the sample has to absorb. The thing you're analyzing for should absorb this light. Today we're analyzing for phosphate. So the phosphate absorbs the light. Let's say 3 photons come in, but only 1 photon comes out. You could say that 33% of the light was transmitted. Again, 33% transmission. Or, if you're talking absorbance, you'd say 2 of the photons were absorbed by the sample. The light hits a detector. It generates some kind of electrical signal. That signal is transmitted to a little scale here. You'll have a little needle that swings and gives you a reading. There's 2 scales on these instruments today. The upper scale is the percent transmission scale. The lower scale is the absorbance scale. What we're really interested in measuring today is the absorbance. However, the 2 scales are really different. Percent transmission is easy to read. Percent transmission, it's a nice linear scale. It goes from 0 to 100% transmission. Nice even increments. So it's very easy to read the percent T scale. The absorbance scale here is weird. Guys, this is a logarithmic scale. So what you'll notice when you look at the instrument, this big distance here represents an absorbance of 0.1. A shorter distance is another tenth, so 0.2. Still shorter distance, 0.3. Do you notice how as you move through the scale, it's not linear? At the very end of the scale, this little distance here goes from 1 to 1.5, and then from here to here is 1.5 all the way out to infinity. So it's a non-linear scale. It's a logarithmic scale. Some people read the absorbance scale directly. A lot of people find it easier to read the percent transmission scale because it's just easy on the brain because it's linear. You can then calculate absorbance. There's a little formula we have. The absorbance of a solution is equal to the number 2, and then you subtract out the log of the percent transmission. So find your percent transmission, take the log of it, you'll get a number. Subtract that number from 2, that's your absorbance. Okay guys, here's the spectrophotometers you're going to be using today. It's called a Spectronic 20. You have different parts of it. You have the on-off switch. You have the sample holder. The thing that's absorbing the light, your sample goes into a little, it looks like a test tube. It's actually called a cuvette. What's a cuvette? An expensive test tube with good optically clear glass. The sample goes in the sample holder here. You see that little needle flying around. That's your needle that gives you the percent T or the absorbance reading. Whenever you do put a cuvette into an instrument like this, you might notice the cuvette has a little line etched in the top. The sample holder here has a little line etched here. You always line them up so they're pointing to each other. That way the cuvette always goes in with the same orientation. That way the path of light, as the light goes through the sample, it's always going through the same piece of glass, and you get much better precision and accuracy that way. This knob allows you to adjust the wavelength of light that's being used. This affects that monochronometer we talked about. And the all-important reading comes from this scale here. And you see here, the upper scale is your percent transmission scale. It goes from 0 to 100 in nice even increments. Whereas the absorbance scale goes from 0 all the way out here to 1.5, and then from 1.5 to infinity. It's not a linear scale. What we're interested in measuring is actually the absorbance. Many people, of course, will read percent transmission, and you just go through that little formula that the absorbance is the number 2 minus the log of the percent transmission. Okay guys, again, the goal today is to figure out the phosphoric acid content in the soft drink. So the phosphate that's in here, the phosphoric acid, doesn't really absorb light. We got a problem. But we're going to do something that chemists do all the time. We're going to take the thing we're trying to analyze for, the phosphoric acid, we're going to turn it into something else that does absorb the light. So if you react phosphates or phosphoric acid with this reagent, molybdate metavanadate, no, you don't have to know how to say that. You mix it with this, it forms a complex which does absorb ultraviolet light. So that's what we're going to be doing here. We'll be mixing the soft drink with this reagent. Now, how do we figure out the concentration? Well, before we tackle the soft drink, we're going to mix up 4 solutions where we know the exact concentration of the phosphate in those solutions. So we have a stock solution or a standard solution of phosphate here. We know the molarity of that. It is 3 times 10 to the negative third molar in phosphate. We're going to mix up 4 different solutions following the guidelines in the lab manual. So for the first solution, it wants us to use 2 milliliters of this phosphate solution. They simply take 2 milliliters, pull it into your pipette. There we go. That will be 2 milliliters transferred into my flask. This is known as a volumetric flask. Volumetric flasks have these long skinny necks. They're calibrated quite precisely, so if we fill the water up right to where the line is, that would be 100.00 milliliters. So we had 2 milliliters of that. For each solution we mix today, we have to add the same amount of this reagent, so 10 milliliters of the molybdate metavanadate reagent. Get our 10 milliliters of the reagent in there. And again, when this reacts with the phosphate, it will start to form a complex that absorbs that ultraviolet light. And this is fairly common in analysis. Sometimes the thing you're trying to analyze for does not absorb the light, but you can turn it into something else that does absorb the light. So there's our 10 milliliters. We then dilute this up to 100 milliliters with distilled water. Can you pause? You don't want to see me doing that. Okay guys, we've diluted up to 100 milliliters. If you've never handled volumetric flasks, to mix stuff in a volumetric, don't sit here and try and shake it like this. It won't work. You put the little penny head stopper in, and you go up and down about 10-15 times. You let the little air bubble do all the mixing for you. That's the proper way to mix things in a volumetric flask. So at this point I have a solution here. The solution I've got here is this first solution mixed up off this table. I've also mixed up the second, the third, the fourth. And you see, you should be able to see that they're getting darker as they go across, because this has a higher concentration of the phosphate. This one has a lower concentration of the phosphate. So again, hopefully you see that this solution is a lighter color. This one on the end is darker, because this one has more of the standard phosphate in it. Okay guys, we just mixed up our 4 known solutions in the volumetric flasks. You have to know the exact molarity of phosphate in those solutions. We mixed them up using the guidelines in the table here. So to find their molarities, you simply use the dilution formula. M1V1 equals M2V2. So the initial molarity, of course, is coming from the standard phosphate solution. So that was the 3 times 10 to the negative third molar phosphate. For solution 1, the table told us to use 2 milliliters of it. M2 is what we're looking for in this equation. The final volume, we diluted all of them to 100 milliliters. So the final volume here is going to be 100 milliliters. You solve this for M2, that will give you the molarity of phosphate in that known solution. You have to do this calculation for each of those 4 solutions. You'll be putting that data, after you get those concentrations, you'll be putting it on page 227 here. You'll be filling this in with your known concentrations. Once you get those concentrations using the M1V1 equals M2V2 formula, you'll be putting those concentrations here as your phosphate concentrations in the known solutions. Okay guys, so before you can take your readings, you have to zero your spectrophotometer. To zero it, you use these 2 knobs. This knob sets it to 0% T. This knob, you can set it to 100% T. Now, you might be thinking right now there's nothing in the instrument and it's showing 0% transmission. Why is that? When there's nothing in there, there's a little shutter that blocks the light path. So right now, no light is coming through. To zero, you take the solvent that you're working with. Today our solvent is water. This is called your blank. It has everything except the thing that you're analyzing for. So it has none of the phosphate, none of the molybdate reagent in there. You pop it in your instrument, and see how most of the light's getting through, but not quite all of it. So we adjust this to read 100% T. A little bit more there. Okay, so it's at 100% T. Now, when I take it out, that little shutter clicks. Now no light should be coming through, so I can use this to adjust it to 0% T. Sometimes it's a little persnickety, but you go back and forth, and hopefully when I go back to my blank, it should go back to 100% T. It's not, so I have to kind of adjust it again. But you go back and forth until you get to a point where every time you put the sample in, it goes full scale, 100%. And every time you take it out, it drops to 0. At that point, your instrument is zeroed. So that's zeroing the instrument. Now, to make a measurement, you simply take whatever it is you're measuring, and again, we're using these known solutions. You wouldn't just fill this tube back up, you would condition it first. So you pour a little bit in, dump it out, then you fill her up, give it a quick wipe before it goes into the instrument. Your fingerprints on the cuvette will change the readings. Pop it in there, and there's your %T and your absorbance for the first solution. You would do that for all 4 solutions, and then you're ready to roll by making a standard curve. Okay guys, now that you've measured the absorbance of your known solutions, you have to make a graph. This is called a Beer's Law plot. Some people call it a working curve or a standard curve. The funny thing is, if you do it right, it's not a curve at all, it's a straight line. You'll plot the concentration of your known solutions down here. You'll plot the measured absorbance here, and if all goes well, you end up with points that give you a nice straight line. You draw your best possible straight line through all those points. That point's a little bit off, but that's okay. Stick with your best possible straight line. That's your Beer's Law plot. Now, what's the idea here? The idea is this. Whatever we did with those known solutions, we're going to do the same thing to a sample of the soda that we're analyzing. Then we're going to take that sample, pop it in the instrument, and measure the absorbance. Let's say the soda gives us an absorbance right here. Let's say that's the absorbance we get for our soda. You come across, hit the line, drop down. That would be the molarity of phosphoric acid in the soda. So you start by measuring the absorbance of known solutions. Make your graph. Then you measure the absorbance in an unknown solution. And as soon as you read that absorbance, come across to that line, drop down. That's the molarity. One reason absorption spectrophotometry is so widely used in chemistry is it's really fast. It might take you a while to make your Beer's Law plot, but if somebody hands you another sample to analyze, you mix it up, put it in the machine, get an absorbance, you know the molarity. They give you 20 samples. You just mix them all up, pop them in the machine. In a commercial lab, you don't even put them in the machine yourself. They have robotic arms that pick up the little cuvettes, drop them in the machine. You don't have to read the graph. They have a computer read the graph. So you can analyze 100 specimens in no time using spectrophotometry. It's a very rapid-fire method of analysis. It's also quite sensitive. Quite often you can get down to very, very low detection limits. You can measure things on the order of nanograms per milliliter in a solution. So it's sensitive, it's fast, it's a great method of analysis. Okay guys, we just discussed how we made the Beer's Law plot. Now, to analyze our soft drink, we want to know how much phosphoric acid is in here. We'll just take a sample of this, 2 milliliters of it. Oops. Transfer it to the volumetric flask. We're going to treat this exactly the same way we treated all of the standard phosphate solutions, although this is our unknown. This here would be our unknown. The other ones were our knowns. So to each one of these, we have to add a 10 milliliter sample of the metavanadate molybdate reagent. After we add this, we'll dilute it up to 100 mils, mix it up, and when all is said and done, it'll look like this. This is our soft drink, mixed up the same way we mixed up the knowns. We then put this in the instrument and get an absorbance reading from this. Okay guys, we mixed up our soft drink. We took it over to the instrument and measured the absorbance. The absorbance came to 0.25, which would be right there, so that's 0.25. Now, again, we want to know the concentration of the phosphate in this. So we come over, read over to the line, drop down. Looks to me like that's about 4.7. So that's telling me the concentration in this soft drink here would be the 4.7 times 10 to the negative fifth molar. That's the concentration of phosphate, not in the soft drink, but in the diluted sample here. What's the concentration in the actual soft drink? To discover that, we have to go back to the dilution formula. Okay, so we mixed up our soft drink, diluted it. We made a measurement, we read our graph. We figured that the concentration of phosphate in this diluted soft drink is 4.7 times 10 to the negative fifth. What's the concentration in the undiluted soft drink? Again, we go back to the dilution formula. We know this guy, M2. That's the concentration after it's been diluted. So that's going to be our 4.7 times 10 to the negative fifth. The volume that we diluted it to was 100 milliliters. The volume we started with, remember when we mixed it up, we used a 2 milliliter sample. And we're going to solve for M1. You're running the dilution formula backwards here. You know the concentration in the dilute material, and you're going to solve for the concentration in the soft drink. You actually do this in analytical laboratories all the time. If you have a sample that's too concentrated, it's off the scale of your instruments, what do? You dilute it down until you can get a reading. And then you can backtrack to find the original concentration. Okay guys, so again, we're trying to get to M1 here. You solve this equation for M1, and you'll end up with 2.35 times 10 to the negative third molar. And that would be the concentration of the phosphate, or the phosphoric acid, in the undiluted soft drink.